This lesson is about the Pythagorean Theorem and other formulas. Using a calculator will help you solve many of the problems in this lesson. You may also want to keep paper and pencil handy to take notes. And remember, the problems you see on the screen are also presented in your study guide. In this lesson, we'll learn about right triangles. A right triangle is a triangle that has one right angle in it. All right angles measure 90 degrees. The sides that make the angle are perpendicular. This symbol shows that an angle is a right angle. Squares and rectangles also have right angles, 4 of them. Other geometric figures can have right angles too. You can find right angles almost anywhere. The corners of most doorways are right angles. The edge of this table is a right angle. Sidewalks intersect at right angles. Right angles and right triangles have many applications in technical fields. But before we look at some of them, we'll first learn more about right triangles. In a right triangle, the two perpendicular sides are called the legs. We call the other side the hypotenuse. The hypotenuse is always the longest side in any right triangle. But the most important thing to remember about the hypotenuse is that it is always opposite the right angle. The corner of the right angle symbol points to the hypotenuse. In just a minute, we'll be using the hypotenuse in an important formula, so be sure you can identify it. In this triangle, side E is opposite the right angle, so side E is the hypotenuse. In this triangle, side R is the hypotenuse. It is opposite the right angle. In this lesson, we'll mostly work with a formula that describes the relationship of the three sides of a right triangle. In particular, it describes the relationship between the lengths of the legs and the length of the hypotenuse. The formula is a squared plus b squared equals c squared. In the formula, a and b are always the lengths of the legs. C is always the length of the hypotenuse. In this triangle, the legs are a and b. The hypotenuse is c. The legs measure 3 inches and 4 inches. The hypotenuse is 5 inches. So in the formula, we'll substitute 5 for c. We'll substitute 3 and 4 for a and b. Doesn't matter which is a and which is b. Now we'll simplify. 3 squared is 9. 4 squared is 16. 9 plus 16 equals 25, which is the same as 5 squared. The formula works for all right triangles. This formula is so important that it has a special name, the Pythagorean Theorem. It's named after the Greek mathematician Pythagoras, who lived about 2,500 years ago. There are a number of ways to use the Pythagorean Theorem. For example, we can use it to determine if a triangle is a right triangle when we know the lengths of its sides. This triangle has sides measuring 15 centimeters, 17 centimeters, and 8 centimeters. In a right triangle, the hypotenuse is always the longest side, so the 17 centimeter side is C. Then the 8 and 15 centimeter sides are the legs A and B. In the formula, we can substitute 8 for A. For B, we'll substitute 15. For C, we'll substitute 17. If the triangle is a right triangle, the left side of the equation will be equal to the right side of the equation. Let's see what happens when we simplify. 8 squared is 64. 15 squared is 225. 64 plus 225 is 289. The square of 17 is also 289, so this triangle is a right triangle. How about this one? The triangle has sides of 9 feet, 16 feet, and 18 feet. It looks like a right triangle. If it is, the 18-foot side will be the hypotenuse, C. The other sides will be the legs, A and B. We'll find out if this is a right triangle by using the Pythagorean theorem. Substitute 9, 16, and 18 in the formula. 9 squared is 81. 16 squared is 256. 81 plus 256 is 337. 18 squared is 324, not 337. This triangle is not a right triangle. This angle looks like a 90-degree angle, but it's actually about 87 degrees. We can't always tell if an angle is a right angle just by looking. That's why anyone who builds or draws must be able to measure carefully. For small distances, you can use a tool with a 90-degree angle, but a tool like this won't give you the accuracy you need if you're working with large measurements. Accuracy is important. Suppose the triangle we last worked with was one side of a support for a roof that measured 9 feet by 16 feet by 18 feet. If you built an identical support for the other side, you'd have problems. If everything else was square, these two supports wouldn't fit together properly. There'd be a gap at the top of the roof. There's another way to use the Pythagorean theorem. If we know we're working with a right triangle and we know the lengths of any two sides, we can find the length of the third side. In this triangle, we know the legs are 5 inches and 12 inches. To find the length of the hypotenuse, we can use the Pythagorean theorem. We'll substitute 5 for A and 12 for B. 5 squared plus 12 squared equals C squared. Now let's solve the equation. 5 squared is 25. 12 squared is 144. 25 plus 144 is 169. So C squared is 169. To solve for C, find the square root of each side of the equation. The square root of C squared is C. Use your calculator if you don't know the square root of 169. It's 13, so the hypotenuse is 13 inches. By the way, since we're working with a quadratic equation, C can also be negative 13. But when we're talking about lengths, we'll only use the positive solution. We can't have a negative length. Here's another example. In this triangle, we know the length of the hypotenuse and one of the legs. What's the length of the other leg? We'll use the Pythagorean theorem again. Substitute 6 for A and 10 for C. 6 squared is 36. 10 squared is 100. Subtract 36 from each side of the equation. Now find the square root of each side. B equals 8. The other leg of the triangle is 8 centimeters. Here's another one. This triangle has a hypotenuse that's 2 centimeters long and one leg that is 1 centimeter long. How long is the other leg? Use the Pythagorean theorem. Substitute 2 for C and 1 for A. 1 squared is 1. 2 squared is 4. Now subtract 1 from each side of the equation. To solve for B, find the square root of each side. B equals the square root of 3. Knowing that this leg is the square root of 3 doesn't tell us much about its length. So we'll use a calculator to approximate the square root of 3. It's about 1.7 centimeters. By the way, the length of one side of a right triangle is often an irrational number. When we work with the Pythagorean theorem, we find the square roots of numbers, and the square roots of many numbers are irrational numbers. There are, however, a few common right triangles where the lengths of all three sides are integers. We've already seen that a 3, 4, 5 triangle is a right triangle. We also saw a 6, 8, 10 right triangle. Its sides are multiples of the sides in a 3, 4, 5 triangle. We call these similar triangles. A triangle with sides of 12, 16, and 20 is another triangle similar to these. The sides of this triangle are 4 times as long as the comparable sides in the 3, 4, 5 triangle. If you recognize that a triangle is similar to a 3, 4, 5 triangle, you can be sure the triangle is a right triangle without using the Pythagorean theorem. Another common right triangle with integer sides is the 5, 12, 13 triangle. A different triangle with sides measuring 8, 15, and 17 units is also a right triangle. Triangles similar to these are also right triangles. Now let's use the Pythagorean theorem to solve some problems. Suppose you go jogging. You jog 3 miles north, then 4 miles east. Your average speed is 6 miles per hour. How much time will you save if you take the shortest route between your starting and finishing points? To solve this problem, we'll first have to find the distance of each route. The first route is 3 miles plus 4 miles. That's 7 miles. The shortest route between the starting and finishing points is a straight line, like this. We don't know the length of this line, but maybe we can find it. This looks like a right triangle. Since you jog directly north, then east, these two lines must be perpendicular. That means that this is a right triangle. The diagonal line is the hypotenuse. Now let's find the length of the diagonal. Since the legs are 3 and 4 miles, this must be a 3, 4, 5 right triangle. The hypotenuse is 5 miles. If you take the shortest route, you will jog a distance of 5 miles. How does that compare with the 7-mile route? 7 minus 5 is 2. You'll save 2 miles on the shorter route. However, we want to know how much time you'll save by taking the shorter route. The problem tells us the rate in miles per hour, and we already know the distance is 2 miles shorter. We can use the rate, time, and distance formula to solve this problem. The rate is 6 miles per hour. The distance is 2 miles. 6t equals 2. To solve for time, divide both sides of the equation by 6. T equals 2/6. That's 1/3 of an hour. That's the same as 20 minutes. Here's another problem with right triangles. Suppose you're taking a short trip and you only want to bring one carry-on suitcase. Your suitcase is 22 inches long and 14 inches wide. It's 9 inches deep. What's the length of the longest object you could lay flat in the bottom of your suitcase? To solve the problem, let's look at a diagram of the bottom of the suitcase. It's a rectangle measuring 14 by 22 inches. The longest object would fit on the diagonal. The sides of the suitcase are perpendicular to each other, so this is a right triangle. The diagonal side is the hypotenuse. We'll use the Pythagorean theorem to find the length of the hypotenuse. We'll substitute 22 for A and 14 for B. The square of 22 is 484. The square of 14 is 196. Adding the terms on the left gives us 680. To solve for C, find the square root of each side of the equation. Using a calculator helps here. The square root of 680 is approximately 26 7/100 inches. The solution means that you could put something about 26 inches long on the bottom of the suitcase. Maybe your umbrella would fit. We could put in a longer object if we positioned it diagonally with one end of the object at the top of the suitcase and the other end at the bottom. Here's a diagram. The line representing the depth of the suitcase and the diagonal across the bottom of the suitcase are perpendicular to each other. This is a right angle, and this side, the side whose length we want to find, is the hypotenuse. We can use the Pythagorean theorem to solve the problem. We'll let the flat diagonal side be A. We already found that its length is 26 inches. The other leg, B, is the depth of the suitcase, 9 inches. Let's write an equation that we can solve for C. 26 squared plus 9 squared equals C squared. 26 squared is 676. 9 squared is 81. Combine terms. 757 equals C squared. Now take the square root of both sides of the equation. Use a calculator if you like. The square root of 757 is approximately 27.5. So the longest object that we could fit in the suitcase is about 27.5 inches. Here's another problem. A store owner wants to hang a sign above her door. The sign will face people strolling down the sidewalk. Here's the view from the sidewalk. The sign measures 3 feet wide and 1.5 feet high. The sign will hang from a chain 3.5 feet long. One brace will hold the chain. Another brace will hold the top of the sign. The store owner wants the bottom of the sign to hang 6 inches, that's half a foot, above the door. How many inches above the door should she put each brace? Let's first find where to brace the top of the sign. The bottom of the sign must be half a foot above the door. Then we'll add the height of the sign, 1.5 feet. 0.5 and 1.5 equals 2 feet. So this brace will go 2 feet, or 24 inches, above the door. Now let's find where to put the other brace. Notice that the building and the top of the sign are at right angles to each other. The top of the sign, the wall, and the chain form a right triangle. The chain is the hypotenuse. The top of the sign is one of the legs. Finding the length of the other leg will help us find where to put the top brace. We can use the Pythagorean Theorem to solve this problem. The chain is C, 3 1/2. We'll let the top of the sign be A. That's 3 feet. The other leg is B, the unknown. The equation is 3 squared plus B squared equals 3.5 squared. The square of 3 is 9. The square of 3.5 is 12.25. Subtract 9 from both sides. Find the square roots of B and 3.25. The approximate square root of 3.25 is 1.8. The chain should be hung 1.8 feet above the top of the sign. If we want to work with inches, we can multiply by 12. 1.8 feet is 21.6 inches. If it's convenient to measure from the top of the door, we would add 21.6 inches to 24 inches, the distance from the door to the first brace. The store owner should put the top brace 45.6 inches above the top of the door. Here's a different kind of problem. A lumber company has an order to mill a large square beam measuring 1.5 feet on each side. The beam will be cut from a large log. A log is measured by its diameter, the length of a line that cuts through the center of the circle. If the beam is milled from a log that's too large, wood will be wasted. So the lumber company wants to use a log with the smallest possible diameter to mill the beam. What's the smallest diameter log from which the beam can be cut? Let's mark the diameter like this. The diameter of the log divides the beam into 2 right triangles. The diameter is the same as the hypotenuse, so we can find the diameter by using the Pythagorean Theorem. Each leg of the triangle is 1.5 feet long. 1.5 squared plus 1.5 squared equals c squared. Square the numbers, then add. 4.5 equals c squared. Next, take the square root of each side of the equation. The square root of 4.5 is approximately 2.12. The smallest size log the lumber company can use is just a hair larger than 2.12 feet in diameter. As we've seen, the Pythagorean theorem can be used to solve problems with rectangles and circles. Here's another example. 3 round pipes are stacked like this. Each pipe is 3 feet in diameter. How high is the stack of pipes? Let's look at the pipes from this angle. To find the height of the stack, we'll have to find the length of this line. Notice it's not the same as the height of 2 pipes. The bottom of the top pipe is slightly lower than the tops of the bottom pipes. How can we find the length of this line? To use the Pythagorean theorem to solve this problem, we'll have to use a right triangle. What about this triangle? The vertical line is a leg in a right triangle, but this won't work. We can't find the length of the other leg or of the hypotenuse. So let's try something else. We'll work with what we know. The diameter of each circle is 3 feet. The radius of a circle is always half its diameter, so the radius of each circle here is 1.5 feet. It doesn't matter where the radius is located. On any of these circles, the distance from the center to the edge is 1.5 feet. We're trying to find the height of this line. Notice that the top part of the line is 1 radius, so its length is 1.5 feet. The bottom part of the line is also 1.5 feet. To find the length of the line segment in the middle, We'll make it one side of a right angle. The other side of the right angle is this horizontal line, which just happens to be the length of one radius, 1.5 feet. Next, let's draw the hypotenuse. Notice that its sides are made of 2 radii, so it's 3 feet long. Now that we have a right triangle where we know the length of the hypotenuse in one leg, we can use the Pythagorean theorem to find the length of the other leg. 1.5 squared plus b squared equals 3 squared. The square of 1.5 is 2.25. 3 squared is 9. Next, subtract 2.25 from each side of the equation. Then take the square root of each side. We'll approximate the value of the square root of 6.75. It's about 2.6. To find the total height of the stack, we must still add the line segments above and below this leg. Each is 1.5, so their total is 3. 3 plus 2.6 is 5.6. The stack is 5.6 feet high. That's a little more than 5 feet 7 inches. Here's a similar problem. Suppose a truck is hauling 6 large drainage pipes stacked like this. The radius of the pipes is 1.5 feet. If the height of the truck bed is 4 feet, will the truck be able to pass under a bridge that's 12 feet high? Let's view the truck from this side. To solve the problem, we'll have to find the height of the stack of pipes. That'll be the length of this line. We know the length of these 2 parts of the line. Each is equal to the length of the radius, 1.5 feet. So all we have to do is find the length of this line segment. Again, we'll make it part of a right triangle. Here's the triangle. This leg is equal to 2 radii. It's 3 feet. The hypotenuse is 4 radii. It's 6 feet. Now write an equation. 3 squared plus b squared equals 6 squared. 3 squared is 9. 6 squared is 36. Now subtract 9 from each side. Take the square root of both sides of the equation. Approximate the square root of 27. b is approximately equal to 5.2. Now that we know the length of this line segment, we can find the height of the stack. Remember, we have 1.5 feet above and 1.5 feet below this line segment, so we'll add 3 feet to 5.2. The height of the stack of pipes is 8.2 feet. Then we'll add the height of the truck bed, 4 feet. The height of the pipes, 8.2, and the height of the truck bed, 4, gives us a combined height of 12.2 feet. Uh-oh. The bridge is only 12 feet high. The truck will have to take a route with a higher underpass or no underpass at all. In the last part of this lesson, we'll use the Pythagorean theorem to solve problems on the coordinate plane. Let's see how we can use the theorem to find the distance between these 2 points. The coordinates of point A are 5, 10. The coordinates of point B are -3, -5. To find the distance between them, we need to find the length of the line segment connecting them. We can do that if we draw a right triangle with the line segment as the hypotenuse. One leg of the triangle is on a vertical line through point A. The other leg is on a horizontal line through point B. These lines meet at a right angle at the point 5, -5. We'll label this point C. Now we have a right triangle. To use the Pythagorean theorem, we need to find the length of 2 sides. We'll start with the leg BC. Since we have grid lines, we can find the length by counting each space between the 2 points. There are 8, so this line segment is 8 units. There's another way to find the length of the line segment. When we have a horizontal line, we can subtract the x-coordinates. 5 minus -3 is 8. Same thing we found before. Now let's find the length of the leg AC. Again, since we have grid lines, we can just count, but it's quicker to subtract. We won't subtract x-coordinates since the line here is vertical. We'll subtract the y-coordinates. 10 minus -5 is 15. This leg is 15 units long. Now that we know the length of 2 legs, we can use the Pythagorean theorem to find the length of the hypotenuse. That's the distance between points A and B. 8 squared plus 15 squared equals c squared. 8 squared is 64. 15 squared is 225. Combine terms, then find the square root of each side of the equation. The length of line segment AB is 17 units. This formula describes the process we just used. It's called the distance formula. The formula tells us the distance between any 2 points. Even though it looks complicated, it's just as easy to use as the steps we followed for finding the length of this line. But when we use the formula, we don't have to draw a right triangle. Here's how to use the formula in the problem we just solved. Let's say point A is x sub 1, y sub 1. Point B is x sub 2, y sub 2. The formula tells us to find the difference between the x coordinates. That's 5 minus negative 3, or 8. Doesn't matter what order we use the coordinates. If we switched them, we'd have negative 3 minus 5. That equals negative 8. That's okay. Since we're going to square the number, we'll get positive 64 either way. We also have to find the difference between the y coordinates. That's 10 minus negative 5. The difference between these coordinates is 15. 15 squared is 225. 64 plus 225 is 289. D equals the square root of 289. D equals 17 units. That's just what we found using the Pythagorean theorem. Try the distance formula yourself. Use the formula to find the distance between the points negative 4, 7 and 2, negative 3. We'll let negative 4, 7 be x sub 1, y sub 1. The point 2, negative 3 will be x sub 2, y sub 2. Now we can substitute these coordinates in the distance formula. We'll simplify the terms under the radical. Negative 4 minus 2 is negative 6. Negative 6 squared is 36. 7 minus negative 3 is 10. 10 squared is 100. 36 plus 100 is 136. D equals the square root of 136. The square root of 136 is approximately 11.7. Another useful formula, called the midpoint formula, allows us to find the coordinates of the point that's exactly halfway between 2 given points. We'll call it point xy. To find the x-coordinate of the midpoint, the formula tells us to add the x-coordinates and divide by 2. To find the y-coordinate, we add the y-coordinates and divide by 2. To see how the midpoint formula works, we'll find the midpoint between the points we looked at earlier. We'll let 5, 10 be the first point. Negative 3, negative 5 will be the second point. Now substitute the coordinates in the formula. We'll find the x-coordinate first. 5 plus negative 3 is 2, so the x-coordinate is 2 over 2. That's 1. Now let's find the y-coordinate. 10 plus negative 5 is 5. The y-coordinate is 5 over 2, or 2.5. The point midway between 5, 10 and negative 3, negative 5 is at 1, 2.5. Try finding the coordinates of the point midway between these 2 points. We'll let negative 4, 7 be the first point. 2, negative 3 will be the second point. Substitute the numbers in the midpoint formula. Now simplify. We'll start with the x-coordinates. Negative 4 plus 2 is negative 2. The x-coordinate is negative 2 over 2. That's negative 1. Now for the y-coordinates. 7 plus negative 3 is 4. The y-coordinate is 4 over 2. That's 2. The midpoint is negative 1, 2. In this lesson, we've worked with the Pythagorean theorem and formulas related to it. If you had any difficulties with the ideas in this lesson, work through it again or ask someone to help you. Otherwise, you're ready for the examples and problems in your study guide.